Alright, so in this question, what we're trying to find out is what are the expected allele frequencies in a given population of the genotype. So what do we expect to find of the AA, what do we expect to find of A lowercase a, and what do we expect to find of lowercase a, which is complete recession. So in our scenario, what we're given is the total population, which is 280, and the recessive population of what in this case are white-eyed flies as opposed to black-eyed flies. The recessive population of 63. Now I've done some of the prerequisites for math here, or made some calculations just so we can get started on the math. In order to find our q squared, which is part of the equation, p squared plus 2pq plus q squared. In order to find that q squared, we actually need to find 63 over 280. So what happens is we're given 0.225, and as I stated, our q squared. Now, in order to find our p, which is the other important half of the equation, we need to actually find the square root of this, which is 0.4743. Now, that's going to be our q, but we need to find this. We need to find this. Well, we already know what our q is. So all we have to do is, over here, write in 0.4743 plus p, which is our variable we're going to be finding, which is where p is our dominant allele, equals 1. And then it's very simple. Just do a little bit of algebra. And in this case, it's going to be 1 minus 0.4743, which is going to equal 0.5257. All right. So now we have our p. Now we have our q. Now we can start working with this, our p squared plus 2pq plus q squared. As a small reminder, p squared, the p's in this equation represent the dominant alleles, and the q's in this equation represents the recessive alleles. So now we can start doing some of the real work for math. So in here, we're going to start plugging in our values. So p squared is going to be 0.5257 squared plus 2 times p, 0.5257 times our q, which we know is now 4743, plus q squared. In this case, it's going to be 0.4743 squared. And a small reminder, if this equals approximately 1, or in essence it's very close to 1, that means our answers are going to be more or less correct. Voila, it's like magic. I've done some of the prerequisitory math again. So here, 0.5257 squared is 0.2763. 2 times PQ is 0.4987. And Q squared is 0.2250, which is the result we actually found earlier, but we need to figure this stuff out. So in this specific question, we have our ratios given. We have ratios found, rather. So what they're asking us here specifically is, what is the ratio of the population that has the genotype of uppercase A, lowercase a? What's our heterozygous dominant population? Well, we know that our population is 280, and we know that the frequency is 0.4987. So a matter of really simple math. What is 280 times 0.4987, which is our ratio? We do that real quick. 280 times 0.4987 9, 8, 7.
Alright, so for homework 17.1, number 1A,
And that equals
gives us a population of
139.63, but of course you can't round, you can't have half an individual occur. So we simply round that up to 140.
Genotype would be 50%
Now, for the second part of the A question,
of the heterozygous
very simple.
allele.
This question is asking
So
us
then,
what are the
out of the whole
two
population, we have to
selection
find out like, the actual expected value
excuse me.
of the population.
What are the
You could
two
do a proportion
other conditions for the Hardy-Weinberg principle to actually
to
apply?
find out what this
Now,
number is.
what we were
for
already told,
heterozygous,
so we can't say,
that would be
was that this population
140.
was
So
large.
that's the expected number of flower beetles that will have the BB frequency, which is black.
And this population was also randomly selected, was also randomly breeding.
What was it? White-eyed. No. This is homozygous recessive. And then, sorry, I obviously I did a bad thing.
Well then, what are some other, or in this case specifically, two types of conditions that are necessary in order for the Hardy-Weinberg principle to apply? Well, that's easy. You simply need to know that this population has no inherent mutations occurring. The reason for this is that if you have a mutation occurring, all of a sudden you have a difference in the alleles, and a difference in the alleles means a difference in frequencies, and our entire ability to find out exact number ratios is completely skewed. And what is another condition for this? Well, in this case, there are no selection pressures present. Now, what does it mean by no selection pressures present? Well, if there's no selection pressures occurring, then that means theoretically every single member of the species in the population, or rather organism in the population, would have an equal chance of breeding because they would be dying before reaching sexual maturity. So, in this case, it allows this population to randomly mate, breeding. There's no pressure. They're all going to be able to mate at some point, and that allows the numbers to again be accurate because what happens is they're going to have an unchanged frequency. That's it.